Alright, so in this lesson we're going to develop and use formulas to find the areas of circles and regular polygons. So first off, just kind of get back to the basics. A circle is defined as a set of all points in a plane that are a fixed distance from a point, which is called the center. A circle, we normally name it using a circle symbol and whatever its center point is. Now again, reviewing what you should already know here, but the diameter is a line segment whose endpoints are on the circle and that it has to include the center of the circle. So in this case, CD is a diameter, and then a radius is half of that. It's a line segment that has one endpoint on the circle and the other is on the center of the circle. Now pi, again, we've talked about pi for a while, but it's the kind of the formal definition of it is the ratio of the circumference to the diameter. Now what we can do with that is if we multiply both sides by the diameter and switch things around a little bit, we get the circumference is equal to pi times the diameter. And since we know that the diameter is 2 times the radius, we can write this as 2 pi r as another option for a formula. Here's the thing about pi. It's an irrational number. Technically it's called a transcendental number, but don't worry about that yet. It never repeats, it never ends, it goes on forever, never, never, never. And the way that the symbol that we use to represent pi, the Greek letter of the alphabet, represents an exact number. Okay? The 3.14159, etc., that's an approximation. And so as I said before, sometimes we want approximations, sometimes we want exact numbers. Leaving things in terms of pi makes it very easy to use the numbers in further calculations. It also avoids having to deal with rounding decimals, and it's a cleaner looking answer to your problem. So a lot of times I'm going to ask you to leave something in terms of pi, but you need to be able to do either leave it in terms of pi or to be able to approximate it. Now as far as the area of a circle is concerned, if you take a circle and you cut it up into a whole bunch of wedges, you can arrange the wedges to make kind of a parallel looking thing. And the more wedges that you make, the closer it gets to looking like an actual parallelogram. And so, because half of our triangles are on the bottom and half of them on the top, the base of my parallelogram is 1/2 of the circumference. And the height of my parallelogram is the radius. Which means if we take our area formula of base times height, so again, the base is 1/2 the circumference and the height is the radius. Now for the circumference, we have our formula as 2 pi r. Well, 1/2 of 2 is going to be 1, so I just have pi times the radius, and we get pi r squared. So this was actually, believed, developed by Archimedes back in the umpteen BC as a formula for finding the area of a circle. So if I want to find the exact circumference and area of a circle whose diameter is 18 inches, well, circumference is super, super, super easy. If you've got the diameter, the circumference is diameter times pi. So if my diameter is 18, circumference is 18 pi inches. Now for area, we have to have the radius. So I'm going to take my diameter, cut it in half, which is 9. 9 squared is 81, so my area is 81 pi. So if I've got a circle whose circumference is 22 pi, I want to find the diameter and the area. Well, to find the diameter, we're going to take the circumference divided, because again, this is just the diameter times pi. So if we lop off the pi, we get 22 centimeters as my diameter. Well, to find the area, we need the radius again, so we cut that in half. So my radius is 11. So 11 squared is 121, so 121 pi square centimeters is my area. Now if my area is 81 pi, I'm going to set that equal to my area formula. So 81 pi equals pi r squared. I can divide by pi. It's a number, so I can divide by it. So I get 81 is r squared. Take the square root of both sides. I get 9 feet as my answer. Okay, now regular polygons. A term that you will probably not have heard before is apothem. This apothem is the distance from the center of a polygon to one of the sides. So it goes from the center to one of the sides at a right angle. Now the central angle is an angle whose vertex is at the center and whose sides go through consecutive vertices. So it's basically a wedge of the polygon. Okay. Now, like we did with the circle, we can take the polygon and we can cut it into wedges and arrange them into a parallelogram. And it's actually much easier because they've got flat sides and everything. And so just like the base of my parallelogram was 1/2 the circumference, the base here is now going to be 1/2 the perimeter. And just like I had the radius as my height, now the apothem is going to be my height. And so the area of this parallelogram is 1/2 the perimeter times the apothem. And so that's basically my formula. And we kind of flip it around just for some reason, I don't know why. And so 1/2 the apothem times the perimeter is my formula. So, since all the central angles have to add up to 360, the measure of any central angle is 360 divided by n, or the number of sides. Okay. And so we kind of get a nice little isosceles triangle here. And so the central angle is going to be my vertex angle, the apothem is the height, and then the base angles are going to be 1/2 of the interior angle. Okay. What this means for you is that we can take any regular polygon, we can create a little right triangle where one leg is the apothem, one leg is 1/2 the length of a side, and we've got 1/2 the central angle as one angle and 1/2 the interior angle as the other angle. Which means that if we know the length of a side, we can find the area of the polygon. And we're almost always going to be using tangent for this. I mean, every once in a while, a problem will throw in this hypotenuse here, but that's usually fairly rare. Mostly we're going to be working with the apothem and the side length. So you don't have to put this in your notes, but just kind of review of where we're going here. If you remember back when we had our table of interior angles and all that other good stuff, you'll notice here it's like for a triangle, each interior angle of a regular one is 60 degrees, so 1/2 that would be 30. The central angle, which would be 360 divided by 3, is 120. We'll take 1/2 that, we get 60, and etc. all the way down. So I've got a regular pentagon here, side length of 10, and I want to find out its area. Well, my perimeter is 5. I have 5 sides. 5 times 10 is going to be 50, so there's my perimeter part. So, but now I have to find the apothem. So I'm going to sketch out the little right triangle. And again, it's usually easier if you just sketch a separate one. That way you can kind of separate out where everything goes. And so we don't know what the apothem is, but we do know 1/2 of the side length is going to be 5. We do know 1/2 of my central angle is going to be 36, because basically 360 divided by 2 times 5, essentially. So 360 divided by 10 would be 36. One of my interior angles is 108, so 1/2 of that would be 54. So I have a little triangle here. So now we can use trig to find out what my apothem is. So you can either take tangent of 36 equals 5 over a, or you can take tangent of 54 is equal to a over 5, whichever floats your boat. Either way, a is going to be about 6.88. We already know the perimeter is 50, so plugging that into my formula, and I get my area is about 172. Now, this is kind of a side note if you like to play with algebra, because you might have noticed here we're plugging a lot of the same stuff in over and over again, and so it's possible to come up with one formula to find the area with just the side length. So I started off with this thing here, 1/2 the apothem times the perimeter. Now, again, this is totally, you don't have to put this in your notes unless you really want to. Here's what I did with it. My apothem is going to be 1/2 the side divided by the tangent. Now here's my 1/2 of my central angle right here. Because remember, if I used the central angle because it's a little bit, the calculation is a lot easier to do just given the number of side lengths. We don't have to go with the 180 minus 2 or n minus 2 times 180, all that sort of stuff. and then finally multiplying it by n times s. Again, if you like algebra, you might want to go ahead and see if you can derive this formula yourself, because it's kind of fun to play with. I had a fun afternoon playing with this thing. And when you clean everything up, kind of simplify everything down, you end up with this thing right here. Now, you may not look simple, but the issue is that if I know the number of sides and the side length, I can plug it into here and get the area, boom, one step. So which is what I liked about it. Okay, so we've got n times s squared divided by 4 times the tangent of 180 divided by n. Plug that into your calculator, boom, you got the area. Which is kind of cool. Alright, so we want to find the area of a regular octagon with side lengths of 15 inches using this new formula. So octagons have 8 sides, each side is 15. Plug that into my formula here, so I get 8 times 15 squared divided by, when you put this in the calculator, make sure you put two parentheses, 4 tangent 180 divided by 8, close your parentheses, close parentheses, and you get 1086.4 square inches. That's kind of cool. Okay, we want to find the exact area of an equilateral triangle. I say exact here because we've got this cute little 30, 60, 90 triangle, so we can calculate the apothem exactly as, again, here's the long leg of the triangle here, so 6 divided by 3 times the square root of 3, and we get 2 square root of 3. So that's going to be my apothem. And then my perimeter is going to be 3 times 12, which is 36. So the area is 1/2 of 2 times square root of 3 times 36. So I get 36 square root of 3. And this actually kind of, if you play with the algebra on this actually leads you to a special formula for an equilateral triangle, which is side squared square root of 3 divided by 4, where s is the side length. And so if you took our previous example, if we plug in 12 for s, we get 12 squared square root of 3 divided by 4, which is 144 divided by 4, which is 36 square root of 3. Yay, it works. And so we don't have to try to draw in that 30, 60, 90 triangle. You just need to remember S234. And so this is a special formula for the exact area of an equilateral triangle. Now, since a hexagon is composed of 6 equilateral triangles, this formula also works for the exact area of a hexagon. We just have to remember to multiply everything by 6. So if I have a hexagon whose side length is 14, I plug in 14 for s, and so I end up with all of that stuff there, and come out with 294 square root of 3. So just kind of the formulas you need to keep in mind. And again, these, you really need to know these down cold. I mean, I will generally give you, I'll definitely give you this lovely thing here. And any formula charts on a, curriculum assessment or anything are going to have your circle and your area and your 1/2 apothem times perimeter. The formula chart does not have the equilateral triangle or the regular hexagon. So those, again, that's a really good idea to memorize these, because, again, that way you don't have to mess with this thing right here. You don't have to mess with using trig to find the apothem. And finally, remember pi r round, cornbread r squared.